is that fine?
No.
No.
Low.
How is that?
You can try with this one or lower. You can. No, the.
No. No. Maybe that's good, but I will check if it's good for the. And like this is still good now.
No, because I have a background.
Like this. It's still good?
It's fine.
C'est comme ça pour les questions. Comme ça, on a une demi-heure. Et je fais comme ça pour le cours. Est-ce que ça vous va?
Non, non.
Parce que ça va impacter la qualité de son. Moi, je préfère que l'image soit bonne. Parce que de toute façon, vous, sur YouTube, vous allez montrer l'image récupérée par l'ordinateur.
Oui, mais du coup, après, c'est vrai que
on voit
la
pas
caméra,
trop les...
c'est vraiment...
Oui, mais ce que filme la caméra, c'est le speaker.
Oui.
C'est ça. Donc c'est pas très grave, Koen, si on te voit pas très bien sur YouTube. Tu préfères que les spectateurs voient bien le... Okay. Voilà. Du coup, on se met d'accord sur... Alors, pendant les questions comme ça, et pendant la présentation... Qu'est-ce que j'avais dit? Moi, je prends pendant les questions comme ça. Et pendant la présentation comme ça.
D'accord.
Ça va?
Après, s'il veut bien prendre... Parce que là, on n'a rien du tout. Vous voyez? Là, on a vraiment zéro lumière.
That's okay.
Like this, it's fine for you, Koen?
Can you try on and off? Yeah, it's okay. Doesn't make a lot of difference because it's front.
Yeah. Good compromise?
Okay.
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 Okay, so only this one for the questions.
Oui, c'est mieux parce qu'il y a des gens devant aussi qui parlent. Comme vous êtes souvent là-bas, c'est mieux que ça soit dans le noir aussi.
Bon, c'est pas très grave. L'important c'est que l'image en est. Mais ok, donc le numéro 2, tac, comme ça. Ok, merci. You use this one?
Yeah.
Only the pointer?
Yeah, I will move. Oh, yes. You know, there is a famous Chicago joke. I know. Not the movie. Hopefully, I have experiment results. Okay. Yeah. So I could send you something. Well, I might come back to that, depending on... It's me. Let's have a talk. Where are you going?
Okay, welcome back. So after a first session in paleontology, we'll have the second session in materials, processes, and chaîne opératoire, so more on the side of artistic materials and chemistry. And the first keynote speaker is Koen Janssens from University of Antwerp, so from the physics department now, very recently. So you probably know Koen, and he has pioneered many methods, synchrotron-based methods, in particular for application in the field of cultural heritage. And what is also very interesting is that he also extended their use out of the scope of synchrotron and with laboratory and portable instruments. And I think he has a huge impact, thanks to this, for the entire community. So I'm very happy and very curious to know about Koen's presentation. So Koen, please, the floor is yours.
Yes. Okay.
You can start.
Yeah. Okay. So, thank you for the invitation, Marine, and the SRF, and Streamline, and whatever. I'm very happy to be here. I think the first time I gave a talk in this room was somewhere in 1996-7. And the purpose was then another workshop like this one, where we tried to convince the SRF management and the Scientific Advisory Committee of the SRF to install a second microprobe beamline. And that needed some convincing, because at that time there was already a microprobe beamline called the microfocus line, ID30. So things have changed now. The people know now that microscopic beams, nanoscopic beams have their use in many areas. Anyhow, this is a bit the context. I would like to show you this picture, or I'm showing you this picture, and I was just sitting next to Francesco, and his first reaction was, beautiful. And indeed, that's one of the reasons, I think, why people like to deal with artworks, because they are beautiful. Maybe not all of them, but I think this one is. So it's an emotional, maybe not scientific and not material-related motivation, but it's a strong motivation, certainly for me. And this is Clara Serena Rubens, the daughter of Rubens, who was painted very lovingly by her father, when she's about 12 years old. So that's one reason, the beauty of art. And of course, if you're a scientist and you know a little bit about optics, you know that this is not real. It's an optical illusion we look at, but it's masterfully painted. So you have to also admire the painter, its technicity, how he manages paint and optical effects to create this illusion. So we also think in Western science, or in the Western world in general, that art objects, especially old art objects, are valuable, must be kept, must be cared for, and that they're scarce. And of course, not everyone can paint as Rubens, so it's a rare object, even though Rubens painted thousands of paintings, but not of his daughter. And the third reason, which is also important, and that's why we are really here at the SRF, is that when you look at this detailed photo, you see the damage to the painting if you have, let's say, the eye for that. Everyone can, of course, see that there are cracks, but all paintings have cracks in them if they have a certain age. But as a chemist, of course, I translate that these are openings in the paint through which gases from the atmosphere can enter and react with the material which is at and below the surface. And if that happens, if you have new chemicals, it can start migrating, because water is also going in and out of paintings all the time, and therefore, for instance, precipitate at the surface or push up the surface and break open, etc., etc. And of course, that is also makes them interesting and makes them, let's say, scientific material to be characterized in detail at different length scales. Okay. So I took this title, Synchrotron Radiation and Cultural Heritage, Quo Vadis. Actually, I'm just going to talk about painted cultural heritage, so that's a bit more limitative. And I always wanted to start a talk with the enterprise, because it's kind of a dynamic thing. Actually, what I did to prepare for this talk, I looked at something Marine already referred to, the previous workshop on cultural heritage that was done at the SRF, and where I also gave a talk, and that was already 15 years ago in 2005. So this was an edition of the SR2A conference. And as you can see here, some of the characters which are there as speakers are now here. They moved up a few categories. I'm still more or less where I was at the time, so that's also good. And then I think a number of people are either here or are following now the broadcast. So I looked just to see what I was talking about then, because 15 years is long. And at that time, I was very much into X-ray fluorescence. I still am, but less. And at that time, microscopic X-ray fluorescence, for which we wanted to create this beamline, was relatively new. We published a book on that in 2000. And so I thought, well, I'm going to explain the use of micro-XRF on cultural heritage, but then with synchrotrons. And one of the first images I showed there was this fish, where you see the distribution of thorium, so an element that has come into the bone of the fossil during the fossilization process. And I like that because it's an image, so it's microscopic, and it's also a trace component that you could see there, and so I explained that as an advantage that you could do trace and microanalysis at the same time. I was at the time also interested in glass, in the color of glass and glassy materials, and the other point I made was saying, well, we try to investigate why this glass is red. That's because there are nanoparticles, but we were doing this in a little bit of a clumsy way by cutting up and looking with a TEM. Anyone can do that. But there is a much more elegant way of doing that. You bring your entire object without sampling it to the SRF, and then you characterize it maybe in an indirect way. You measure interatomic distances with EXAFs. And this had been on the cover of the SRF newsletter around that time. Other things, and that's why this meeting I will always remember, is that I met there a Dutch colleague, Joris Dick, who looked very young at that time. And of course he was young. And he was talking, or I showed that he had been in Nature talking about discoloration of pigments. Here you see smalt, so a glass with cobalt in it that can lose its color. And I said, well, this is really an application where you have to use the SRF because you can figure out what's happening there. I also mentioned this as an important development in XRF. And I see now with the knowledge of hindsight that that was a little bit off. This was very attractive, looked very attractive. You could look below the surface of paintings, but this method has never broken through. I believed in it for a number of years, and some other people do, but it is never really going to make it, it seems. But other things I was more lucky in predicting that they would be successful. For instance, here this work by colleagues from Barcelona, who were using then small beams to look at individual paint layers in cross-sections and doing in transmission XRD. And then, for instance, this is about copper, copper greens in these Catalonian altarpieces. They found all kinds of stuff, and I thought, wow, this is really fantastic. You can see all this information. This is something more we need to do. And that turned to be true. They did this at SRS, the old English synchrotron in Manchester. And I remember that very well. And in the same vein, I said, well, the next step there is to start not just measuring a few points, but measuring many points here on this Roman fragment of a fresco. And that had been done by a number of people from Paris and from here, Jean-Louis Rodot, I've seen him around. And I thought, I said, well, you cannot only do mapping here, simple elemental mapping as we do with XRF, you can also do this with the crystal phases. And then you're really busy with the pigments themselves. That's really interesting. And so this was the first image I presented there, or I referred to them, and this was done at ESRF ID 21. Okay. So now we are today, and while for gathering all these cases together, I remember having a lot of work trying to find all kinds of sources. Now, of course, the literature is more accessible, and also me and other people have written regularly reviews, and a number of them are listed here. And my interests, let's say, have narrowed down from a more general idea or a more general activity on different types of cultural heritage materials and other materials, more or less exclusively to paintings and painted works of art. And so I was therefore also very happy on the occasion of this workshop to see this another edition of Synchrotron radiation use with the review of reviews, let's say, written by Marine and a number of colleagues and Paul Taffaro. Okay. So if you look in that article, I was also very pleased to see that the number of works of art that we looked at in the past were mentioned there. And one of them I would like to start with is this cadmium yellow degradation, which at first looked to be an easy case. Why was that? Well, some yellow areas of paintings, like here this Enser painting, showed a superficial precipitation which is colorless to white. And this is from a museum in Holland. And Joris Dick, who I knew by then, had tried in Delft, which is a technical university and very well into material science, to use TEM to figure out what this white powder was. And this didn't work because the electron beam evaporated the white powder. So very destructive, a lot of energy dissipation there. So I convinced Joris, okay, let's go and find Marine and ID21 and see what happens. And yeah, with very little effort, we could see that, or we could make the difference between the sulfide, the original state of sulfur in the cadmium sulfide, which was yellow, but we also saw very quickly that there were a lot of sulfates there. And then by doing a few XRF maps at these three energies and manipulating a bit, we could produce this very clear picture of an oxidized crust on top of the original pigment. So you could call this low-hanging fruit. It didn't require a lot of efforts. The experimental setup was there. We just had to use it. And with one image, we had the clear message that could be published that the sulfide became a sulfate, and even a very simple chemical formula there. What we didn't know was that we only thought that this was a simple situation. This kept on going. We collaborated with more and more people and published more papers, as you can see here, and we ended up with looking at more famous paintings, like here, Le Bonheur de Vivre. But as Laetitia Monico will explain tomorrow, this story has become more and more complicated, and maybe now we start understanding why the cadmium sulfide sometimes oxidizes and sometimes not. But I will leave that to her to explain tomorrow. What we also learned or noticed that if we go through this layer here, or this series of paintings and problems, that actually most of the materials we were looking at which show the discoloration, spontaneous discoloration, were semiconductors, were activated therefore by light. And then we also learned that there are different subtypes of semiconductors, some of which sometimes push up the freed electrons or suck down the freed electrons, depending on how the bound and the anti-bound states, how the conduction and the valence bands are bent near the surface. And with that relatively simple picture, things also became more understandable. It was not just in individual materials that did something. We could more or less start predicting when a particular reaction would happen. And if you give this, even this simple concept to a systematic scientist like Laetitia Monico, maybe sometimes a lot of possibilities of reactions show up, and this was published then a bit later. But we could draw from the area, much more developed area of semiconductors and especially of solar cell chemistry to understand what was happening there. Again, I will not go into that. Laetitia will visit this again. So this graph, where we consider a little bit band bending, etc., is in another article in the same number which we wrote in Antwerp. All right. So we moved relatively quickly from what looked like simple situations, one chemical transformation and therefore one method like Zane's, to use towards much more complex things. So we're in this area of complexity, as Francesco was saying, and that is, of course, then required that you use several methods. And one of them, X-ray diffraction, has in the meantime stolen my heart, because yeah, it fits very well the problems we look at. Huh? And one of the other sulfides we looked at was also addressed already by Marine, also in publications dating to 2006, is now mercury sulfide. So mercury is below cadmium in the periodic table, so you could say, well, it's a similar problem, but that turned out not to be the case. And in her exploratory investigations, Marine already pointed out that chlorine was involved, which complicated things. And we, from our side, we started to investigate, let's say, some home samples by the painter Rubens, where you clearly could see that the red became black and sometimes the black became white, or the other way around. And the same could be observed in these Pompeian and Roman fresco samples. Turns out that there, actually, by using the much more specific method of micro-XRD, we could puzzle out that actually in transforming the red pigment to something white, like calomel, which is a chloride, a mercurochloride, actually you have to pass through a number of steps, and those steps involve the formation of fairly exotic mercurosulfochlorides. Not one, but three. Two of them which are known in nature, gamma and alpha, which are corduroite and kenchoite, which have mineral names, and then some beta form, which is even more exotic, that somebody, luckily, in Siberia synthesized in the lab and characterized with XRD, so you could recognize it. Yeah. But the nice thing was that we found this sequence of layers on top of each other, which we interpreted as this sequence here, converting the red into something whitish. All these things are a little bit whitish in color, or sometimes a little bit colored, but they are never black. So the mystery there was, for a long time, for several years, what is the black compound? And we found that finally, after publishing some results, by trying to form it again, by shooting on the red pigment with a laser, a blue laser, from the thoughts on the semiconductors, in the presence of chloride ions, then we could reproduce that, and this turned out to be elemental mercury. So then we were in the press saying, the paintings of Rubens, they bleed nanodroplets of liquid mercury, things like that. Anyhow, so this completed more or less the sequence, but I remembered from that, yeah, things can be complicated and one transformation can follow another, and if you only have the front and the behind, it may be difficult to reconstruct what is in between. All right, and then we published some more on the thermodynamics and on the kinetics of all this, which can make the picture a bit more complicated. All right, so we did that on the sulfides, also on arsenic sulfides, and on some other things, and this is still ongoing, and we worked on various modern and not so modern paintings. And what came out every time we did that, because next to analyzing originals, so little bits of paint taken from these paintings, we also tried to recreate. So we were making mock-ups, we were synthesizing or making paint and then aging it. Are a number of questions which always come up. For instance, if you have a limited number of very small samples, how representative are they for a very large painting? That's an obvious question. But also, how fit for purpose are the mock-up samples? We try to create mock-up samples as closely to what we thought the paint was, but this is always an approximation, and you can also create mock-up samples which react in a quite a different way than the reality does. It's another problem. Then there is, of course, the analyst's problem of, do we see everything that is there? Are we missing something important? And then finally, are we changing the sample while analyzing it? So these are a number of fundamental questions that keep on coming back. I will only address actually the top one, because we were fairly active in that, and I think tomorrow some other colleagues will address some of the other ones. So in these two papers here, one written by Costanza Migliani and one by Victor Gonzalez, which is in press, actually the theme is described of using or exploiting different length scales. If we're analyzing paintings, we go from meters, several meters, down to the atomic scale, with different methods and different considerations. And by using them together, you can improve your insight into what's happening. For instance, here on the sunflowers by Van Gogh, we did more or less the entire gamut. We did micro characterization of the entire painting with XRF. We looked at a number of samples with different methods. Then on the nanoscale, you can look at nanoparticles of lead chromate, the chrome yellow in here with TEM. And then on the atomic scale, you can, for instance, do DFT calculations to figure out some stable or not so stable configurations. And a bit less full range is going on now, for instance, on what's happening to lead white components, where certainly the macro and the micro level can be confronted with each other and the insights combined. So, but of course, you need to be able to have especially this macro XRF or this macro level, if only to select the right samples. If you know that in a painting, a very large painting, there are different chemical transformations going on, and you have to select a few points to sample, if you have that choice. You want to, of course, select the best ones. And so we started developing, and here are some of the main characters there, Matthias and Joris Dick, now all together in Delft. We started developing scanners which allowed to, let's say, look at the distribution on the meter scale of painted works of art. I show this here with the sunflowers. So with these XRF maps, you can figure out, for instance, by looking at the arsenic and the copper distribution, that all the green here in this painting is made with a pigment called emerald green, where these two are together. You can look at where the mercury is that Van Gogh used to paint the darker yellow flowers. And of course, you can look at where the chromium is, etc., because that's a major component, a major metal in this very yellow painting. However, only using elemental maps is not enough, because it brings you to the brink of identifying, but doesn't allow you to definitely identify which pigment is there. And again, I think Laetitia will talk tomorrow about the difference between these two. And so we were motivated to go there also in this microscopic mobile world, not only to stay with one method, but to go towards X-ray diffraction, my favorite microscopic analysis method, but try to make a microscopic version on that. So in the chrome yellow world, let's say there is a green one, a safe light fast variety. This is normal lead chromate. But there is also a not so safe or a light sensitive version which contains sulfur. And to see that difference, X-ray diffraction allows you to do that. And therefore we could, in individual strokes made by Van Gogh to paint these sunflowers, we could map that out. And what we are doing by knowing where the light sensitive and the light fast pigments are, we can more or less tell curators these parts of the painting, this is where you have to pay attention to, and maybe from these parts we would like to have some samples, please, and not of the rest. All right. So this micro X-ray powder diffraction we can use in transmission mode. That's relatively easy. We put an X-ray tube in front and a detector in the back, and as X-ray tube we just don't use the entire beam. We have a monochromator that's also focusing, so that we have about 100 microns here, which is very big in synchrotron terms, but the right size for meter-sized objects. And so then we sample with XRD all the layers that the beam is going through. But of course, that doesn't work if you have a very thick wooden panel, as you can see here, because then the beam would not go through completely, or would not go through at all. So we have more recently developed this kind of reflection geometry, where the detector and the tube is all on one movable stage, and we can move that in front of very large panels. And while maybe somewhere in the future, perhaps, another Van Gogh will come to a synchrotron somewhere in the world, I can tell you this panel here will never leave its museum. It's in Ghent, it's being installed today, again in the cathedral, and it will stay there for the next 30, 40 years probably. So either you do something with it there, as a preparation for a synchrotron experiment, or you cannot do anything with that. So in this reflection mode, if we use lower radiation, we also stay closer to the surface, where then all kinds of degradation products are formed, and that's also interesting for studies like this. So the panel I just showed you is the central panel of the Ghent altarpiece. case we have been looking at is Dutch art. So you see here the girl with the pearl earring by Vermeer. It's a 17th century iconic painting, very much smaller than the Ghent altarpiece. And we have this lead map here, which shows us more or less where pigment or paint losses have been suffered by the painting. But there too, we've been doing some macro characterization in combination with microscopic characterization of paint. So you get an impression here of how our computer screen looks like while we're doing that. And it's more or less the same idea there, that we see the normal components of the paint. For instance, you can look at the blue scarf here of the lady that's painted with ultramarine blue. So that gives you a clear signature. And we see the same degradation products as on the Ghent altarpiece, some more maybe. And again, if we look at this hydrocerussite-cerussite ratio, we see actually two categories. We have the light parts of the paint, of the portrait, and the darker ones, the shadows. And this prompted us, so you can figure this out, there is a big difference between these two. But not only that, if we use this scanning XRD, we also get a sense of where below the surface the components are. Because there is a small shift in the diffraction pattern when things are deeper than the surface. So we figured out that actually here, when you look at what is here, light blue, so the light parts, there is nothing special going on. The one component, this lead carbonate, is more or less on the same average depth below the surface than the other component, so that's okay. But here in the shadow parts, they're different. There is a distinction in depth. So we feel this, but we cannot really touch that in a very quantitative way. And so a small miracle then happened, you could say. We told that to the conservators, and they agreed to sample where the things should be sampled to get a view on these two layers. This took some convincing and also searching for positions on the painting where there was already damage, but they did do that, and we did analyze them at Petra, PO6. And for instance, here, the sample from the upper layer shows actually optically maybe a small distinction. Also a distinction in hydrocerussite content, which is just a distinction between the base and the ground layer and what's on top. So nothing really special. And that's what we expected also from the macro scanning. But here you see that there is another stratigraphy. There is a thin layer on top, and the thin layer has quite a different hydrocerussite content, which we now call the scumble layer, than what is below. Yeah? And so by searching around microscopically and then confirming and detailing with synchrotron beams, we can build up this more complete picture. Okay, I will skip a little bit the details here, but what we concluded here is that Vermeer A had different kinds of lead white paints at its disposal and used them intentionally. He was not just mixing up things, he used them, and I think Victor will probably explain a bit tomorrow what the optical properties are and why he used them in this intentional way. Okay, this has been published in the meantime. So what I've been giving you examples of is a kind of sequence of using simple to more complicated methods which end up at synchrotrons. And you could see that as a kind of sample selection procedure. We want to select those samples which tell us the most compelling story and spend our synchrotron beam time on that and not waste time on others. And then, of course, these kind of macro methods of increasing specificity are relevant. And of course, they build motivation to convince museum people and conservators to collaborate and help. Of course, then, now that you have this EBS and you're rethinking access models and the Streamline project, etc., you could, of course, then wonder where in this sequence of events the ESRF should play a role. Of course, it plays a role at the end with the X-ray methods, and maybe with some others. There are some other equipment around here that helps the user. So this is the traditional role, and the distinction could stay there. Then, obviously, if the users need to do all this pre-treatment and pre-selection, you need a little bit of tech users, expert users. They're here, they come here, so that's fine. But of course, you could also imagine that you use a bit more, another division of the roles, that ESRF not only plays its traditional role in micro and nano characterization, but maybe also helps to characterize on the broader scale the paintings which have interesting characteristics. I've put there this crocodile because this morning Paul Taffero showed this very big wrapped up crocodile which they're analyzing and characterizing to be able to focus on very small details in the stomach of the crocodile and then on teeth in the mouse which was eaten by the crocodile. So the question is, my question is, should the ESRF do something like that too, or are there very good reasons not to? There are reasons pro and contra, but apparently in the paleontological field, it's being done. Huh? So this is an open question, but it's interesting to try and answer that. And actually, if the ESRF would move up its area of activity towards pre-characterization, maybe a larger variety of people could come here with their problems or their problem paintings or whatever. Of course, the issue that remains is, will the artwork get here? Huh? Apparently, unique paleontological samples, very big ones, can get here. So some paintings will also get here, that's clear. Huh? Maybe not all. All right. The other point I would like to make before I finish is that you may not have noticed, but while we were listening to the paleo talks, it was full of movies, huh? Full of 3D data sets we were looking at. I did not show any movie. It's all 2D, yeah? Because we cut up samples, and that's fine. Actually, these are also 3D data blocks, but the spectral dimension is so fascinating for the chemical people among us that we are fine, or we think we're fine with 2D data sets. Nevertheless, I think what should be done is that these two modalities merge more or less, and that also in the cultural heritage sector, we go towards spectroscopic tomography. So not just absorption, phase contrast, but XRD tomography, XRF tomography, typographic tomography, etc., to not be able to slice up samples. Because the samples are also unique. Eh? The works of art are unique. The number of samples you get from them, even if you're very motivated and dedicated, is limited. So why cut them up? Maybe it's better to preserve them, analyze them as non-invasively as possible, but nevertheless preserve them. And so a simple question here, for instance, is there are techniques which are used in material science, for instance, for mapping grain sizes, which are diffraction tomography. I'm not aware that anyone in the cultural heritage world has used this or have tried to use this. Maybe there are some reasons why it doesn't work, but we should certainly try. Huh? And one small remark is, of course, that when you do that, when you start doing that on lead-rich materials, and a lot of painting materials are that, you should escape, let's say, from the boundaries imposed by the rhodium coatings on the K-beer mirrors. Huh? Rhodium is at 22, 23, so everyone is below that. That's a limitation, not for XRD. You can do that with 40 keV as well. So somebody should push for that we can start doing this, and of course also scanning nano XRD at really higher energies. All right, I think I will skip this. What I made as points is that we need highly specific methods, several ones. Usually we use them in 2D mode. We should not do that. We should go to 3D and get higher dimensional data. And the pre-stage, the macro stage, is really useful. It's not in the mission maybe of the SRF, but it's in the precursor and maybe useful. All right. I will end with this very nice picture. This is where our sample selection funnel is at the moment. It's in Amsterdam, in the Rijksmuseum. The most important artwork of Holland is there. And yeah, we are trying to find reasons to convince the people that take care of this wonderful work of art, which bits, let's say, might come to a synchrotron. And we already have some beam time for that. Thank you.
Thank you, Koen. So we have some time for comments, questions.
So you mentioned the 4D, and yes, at the beginning of your talk you spoke about confocal fluorescence.
Yes.
Do you think that it would be time to revive a bit the confocal fluorescence to go for the 4D in your paintings? Because it's a way to have the third dimension without rotating these large and flat objects, because the geometry of painting is really very bad for tomography.
Well, I think already in the years up to now, a number of people have tried that. There are a few snags. If you do fluorescence imaging, you cannot choose the energies of the signals that come out. Some are in the right energy range, some are too low, and therefore you become blind after a while. I think this is really a limiting factor. So I much more like the diffraction, where the Rayleigh scattering just keeps you at the same energy level, and a lot of sources of uncertainty are eliminated by that. That's one. I think also there is a problem with the optics. So the collection optics you use for the confocal, there is a lot of optics for producing very small primary beams. On the collection side, you could use the same, maybe that would be terribly inefficient. So that doesn't really work. There should be some breakthrough on the optics on that side, and I don't see it happening. On the X-ray optical side, at the moment, there's not a lot of evolution. So I think it will just stay where it is now. Occasionally, this is useful if you're lucky, if the element you're interested in has a fluorescence line which is high enough and not too high, and if the resolution you need is more or less okay with the secondary optics. But it's not robust enough, I would say. I think with with, let's say, powder diffraction tomography, you will be able to have a much more robust situation, which can be adapted to much more different requirements and situations. And there is this, the Paulson approach, where you do the full field diffraction, which also may be useful and more efficient than the scanning approach.
Other questions?
Well, just a comment, I suppose. In the material science case, then we often have the luxury of making the sample be a cylinder for some of those techniques. But I think perhaps in the Rembrandt and Vermeer case, you can't easily obtain a cylindrical sample from
no,
these
and
to make
probably if you consider, well, are you talking about samples or about the objects?
I was thinking of the techniques in which you talk about diffraction tomography and that sort of thing, which we are used in material science. Yes. Then either the experiment is designed to make a cylindrical sample, or we cut a cylindrical sample from a manufacturer.
I don't know whether that's really a problem. I mean, micro samples, they're rarely cylinders, but they start off as paint chips. They're quasi-cylinders. I mean, their aspect ratio is not very big.
Okay, so you're not thinking of applying it to in situ to some
well,
portion of the panel?
Well, the in situ business is something else still. There, I think you are into the incomplete tomographic collection business.
Yes.
And that works to some extent. Medical people use that with tomosynthesis, etc. That has not been tried with spectroscopic forms of tomography. I think there the time requirements are a bit limitative. This scanning we do now, so our one projection takes a while. So if we have to do this under different angles, it would be very long.
Yeah. Okay, thank you.
Okay. So unless there is any other urgent question, I think we can thank again. Very last one, sorry.
Please visit our poster also.
You've shown this nice example of using peak shift in diffraction to get some depth information. How much resolution do you get in depth?
The effective depth resolution.
Yeah.
It's limited. It's of the order of several hundred microns. So it's only when we see very big differences, so two paint layers which are on different sides of the same parchment, that we see that. Yeah. And so when we would do that, let's say at the synchrotron, where the beam divergence is less and therefore the peaks are sharper, there are some possibilities to do that. Yeah. So for instance, at your beamline with very high resolution, I mean, we could touch upon the real limits. Huh? Yes. Now with this 5 milliradian primary beams we use, which are meant to be small but not too divergent, or too parallel, yeah, it's not optimal. But there is some there are some possibilities there. Yeah.
Thank you.
Probably something to discuss on Friday. Yeah. Probably. Okay. So if we want to keep in the schedule, I think unfortunately we'll have to stop the discussion now, but it will continue and we will have many presentations also related to painting, so we can continue the discussion all together. Thank you again, Koen. Yeah. So we will switch from paintings to stained glasses, and the next talk will be given by Marti Beltran from Barcelona.
It works? Yeah. Well, thanks to accept my lecture about modernist enamels that forms part of my PhD on 19th century enamels in Barcelona that is directed by Trinitat Pradell. The aim of this lecture is to present the results of our research done about late 19th century and early 20th century historical enamels, as we know as Art Nouveau, but in Catalonia is known as modernism. An enamel is a thin glass layer applied and fired at a lower temperature than the underlying glass. In the period, the glass used was a blown glass of the type soda lime, and the enamel it has a vitreous part to which colorants or pigment particles are added to give color. Here we have the different materials that we have analyzed in the process of the project, and all the materials have been keenly sampled by Josep Maria Bonet Vitralls, that is a stained glass workshop from Barcelona that was founded in the first years of the 20th century. Okay, the materials that we have analyzed, on one hand, we have the raw materials acquired by Bonet workshop to the Rigal and Granell workshop. That was one of the most important modernist stained glasses workshops in Barcelona. With the help of the Bonet stained glass makers, we have prepared the enamels that, well, we have apply the powder mixed with water and with a brush over a blown glass and firing at 590 degrees Celsius. The replica enamels prepared were analyzed in the glassy part, the colorants, the reaction compounds, and the pigment particles. Finally, we have analyzed the fragments from historical enamels, stained glasses that have enamels obtained from the restoration of different buildings in Barcelona. The stained glasses were used as functional windows, and they have been exposed for more than 100 years to the weathering and solar irradiation. The degradation of the 19th century enamels is evident. We can see on this picture that we have a crackle in the blue enamel. And the determination of the origin of this enhanced degradation on blue and green also was one of the most important reasons to begin this project. We have used laser ablation, inductively coupled plasma mass spectrometry to determine the enamel's chemical composition. As SEM, EDS cannot detect minor elements and has particular problems determining boron, was one of the principal issues of the method with this kind of materials. SEM was used to determine the composition of the microcrystalline color pigment particles, and FIB to polish the surface in order to obtain high resolution images of the nanoparticles. Ultraviolet visible near-infrared transmittants and diffuse reflectants were used also to determine color, the lab coordinates, as well as the absorption in the near-infrared regions. Microdiffraction patterns were obtained from thin sections of the enameled glasses at the MISPD beam line at ALBA and working at 29.2 kiloelectrovolts. It's essential for determination of degradation products, reaction compounds, and pigment particles on historical enamels, because the samples are small and the enamels are very thin layer and are lead rich. With the laboratory diffraction, we don't have enough energy to analyze with this kind of materials. Thin cross sections below 100 micrometers thick of the samples were prepared, first embedding into epoxy resin coating with a low speed saw with a diamond disc. In the 19th century, European scientists developed and produced a new formulation for enamels. In the forefront was the French chemist Adolphe Lacroix, who wrote a treatise about the enamels, but also other companies like Wengers or Los Piet. We have analyzed raw materials from the three companies, Lacroix, Wengers, and Los Piet. They developed a new formulation based on a lead zinc borosilicate glass with low softening temperatures and a reasonable resistance to water corrosion. In this table, we show the results from the laser ablation ICP mass spectroscopy on the enamels prepared from the 19th century raw materials. The composition of the vitreous part is this one, and we can see that we have a high amount of boron and lead. It's really rich in these two elements. And well, it is the most important is the glassy part of the enamel and the part that gives the properties of resistance to the corrosion. We can see that we have almost 10% in weight from the lead of approximately 40–50%. Boron is 20 more or less, with some variations. silica is really low in this case, and then zinc it's 10% more or less as an example. The colorants, we can see that for example the purple is a purple of Cassius that is an alloy with silver and gold co-precipitated with tin, as appears in modernist recipes from Lacroix and Rigal. We have the amount of gold and silver and tin oxide. We have also selenium red that was really new for the period. That the pattern of the process was really the same years of the production of these materials. We have red of manganese, yellow of chrome. We have, for the greens, cobalt and chrome aluminates, and we have also copper dissolved in the glassy part. For the blues ones, we have also cobalt aluminate particles. As we can see in the SEM image, we have due to the low density of the particles of cobalt aluminate, they form a layered structure of the enamel. Okay. Then we have a part in the surface that is rich in cobalt aluminate particles. We have an interface that is rich in lead, and then we have the soda lime glass that is the base glass of the enamel. Now we will present here the results obtained for some historical enamels from several buildings in Barcelona. Here is an example we have analyzed that is they are produced by the same workshop, Rigal and Granell. It's important to remark that the enamels of the Rigal workshop were in the exterior, these two ones, the PJ1 and the SM1, and the enamel, the NEN1, was indoors in a building in Estació del Nord. It was made also by Maumejan workshop, that it has a workshop in Barcelona. Well, we can see that the enamels that has been in the exterior, they have the glassy part really depleted in boron, zinc, and lead, and is enriched in silica, sodium, and calcium. Okay, we can see that the enamels that has been indoors, they have a proportions of the glassy part that are more or less the same that we have found in the samples analyzed. The first sample, this is one, PJ1, is a purple enamel with some contour grisaille over a transparent glass fragment from the Palau de Justícia. And as I say, we can observe that lead, boron, and zinc has been depleted, opposite to silica, sodium, and calcium. Here we can see also the SEM images of PJ1, and we can note the presence of 3 layers. A1, that we can see the suspension of particles of gold and silver and tin oxide. We have here again the interface that is enriched. Here we have the analysis with ECM, and here we can see that it's still we have the colorant. Here we can see that is enriched, the interface enriched in lead, and here we have the base glass. Okay, we have a soda lime glass. Here we can see the ECM images of PJ1, and we can note the presence of lead sulfate. And that is a result of the lead leaching in presence of humidity and atmospheric pollution. Here we have the micro diffraction patterns of the PJ1 grisaille taken near the surface and the base glass respectively. shows the presence, we have here the surface and the glass, and shows the presence of calcium and lead sulfate, results of the same process of corrosion. The grisaille particles are an iron-rich spinel containing manganese and copper, and iron-rich lead silicate mixed with a purple enamel. The addition of copper oxide reduces the amount of hematite formed and gives a green hue to the glassy part. Here we have the second sample that is also from the Rigali granule, and we can see again that we have depleted in boron and zinc and lead and enriched in silica, calcium, and sodium. It's from the district of Sans-Montjuic. And we can see here the chemical composition and the SEM image of the SM1 that shows the presence of particles of cobalt and chrome aluminate, that are these ones, and melanotechite, that is because that is mixed with the enamel is mixed with the grisaille. Here we have the third sample, and we have a yellow of chrome and copper, and we can see in the SEM images that the enamel is fully amorphous, and is virtually unaltered. Okay. Here we can see the UV near spectra of the studied enamels, and we can see that they show an enhanced absorption in the near region due to the cobalt aluminate particles. Okay. The enhanced absorbance of the infrared light by particles and color centers in the enamel will be responsible for the increase in the overall temperature of the enamel submitted to solar irradiation, as well as for the thermal mismatch between the pigment particles, enamel glass, and base glass. Thermal stresses will cause the formation of cracks due to the mismatch in the thermal expansion coefficients and a faster, greater deterioration of the enamels. To end, for the conclusions, we have the historical enamels compositions have been determined, as well as the composition and colorants of the raw materials of the Rigal and Granell workshop. Microdiffraction is essential to determine the pigment particles and degradation products of samples due to the thinner of the layers. The diffraction is not enough with the samples historicals. With the replicas is enough because we have a big amount of the enamel, but with the historical ones not. And then the study has allowed us to determine the main mechanism of alteration, atmospheric corrosion driven by humidity. The enhanced deterioration showed by the blue and green enamels has to be related to the presence of cobalt aluminate particles, which are responsible for the layered microstructure in the enamel and also for the enhanced absorption in the infrared radiation, and the mixture of grisaille paints or other enamels, because the mixture changes the chemical composition of the glassy part of the enamels, affecting its stability. And that's all. Thank you.
You showed in some tables that you had gold and silver together, and you said, "Oh, it's co-precipitated with tin oxide."
Yeah.
Is there a specific indication why you say that it's a co-precipitate? Because I could also imagine that there are all kinds of nanoparticles in this glass giving the color.
When we put the analysis with the SEM is in the nanoparticles, it appears that is gold, silver, and tin oxide. And well, is the classical.
There's no separation. You always see them all together.
It seems that it's together, and it's the classical recipe of the purple of Cassius. is as its nature. It's like yeah. One moment, I'm going to find the. Okay, we have here, no, the particles, and yes, when you are going to analyze every particle, you find the three elements.
Okay. Yeah.
Thank you. Any other question? No. Okay, so thank you again, Marti.
Thank you.
So the last presentation of this session will be given by Elena Tereschenko, who is coming from Kurchatov
You can take this one.
Institute. And in her talk, Elena will give a bit different point of view as she will show us the complementarity between synchrotron techniques and neutron techniques for the analysis of artworks.
Good evening. It was very. No. Okay. Good evening. Is it working? It was a very long day. So I try to be very short. First of all, I would like to say thank you for organizing committee for inviting me. It's very pleasure for me to make a talk in this auditorium. As you see, I would like to take your attention in a very interesting problem. Sometimes, and you can see it from, we see today a lot of presentation where discuss some problem with imaging. And some of these problems containing with specific interaction of synchrotron radiation with matter. And one way that we can use for solving this problem, it's involve in our study another type of radiation, I mean neutrons. And we use infrastructure of Kurchatov Institute. It includes synchrotron source Kurchatov and neutron source reactor IR8. Of course, we involve in our study wide range of lab equipment, but my presentation will be concentrate only these two results that we received on these two mega science infrastructure objects. Of course, the advantages of synchrotron radiation neutrons, it's a different contrast for hard and light elements. It allows us to separate metal base, for example, and see some corrosion or some organic component in our artifacts. Very significant factor, different value of penetration depths for these two type of radiation. Not exactly radiation, but with synchrotron radiation and neutrons. And base experimental techniques that I will show today. It will be imaging and elemental and phase analysis. And the main issues of our study, it's inner construction or outer appearance of our objects of cultural heritage for reconstruction of the technologies of their production and the estimation of their preservation state. I have only 15 minutes, so I will show only few examples of our research. It's some metal items of medieval period from State Historical Museum collection, and some artifacts from the excavations of Institute of Archaeology, Russian Academy of Science. First of all, metal artifacts from medieval burial mound, Черная могила or Black Grave. What is that monument? This the biggest burial mound on the territory of Old Rus, dating 10th century. And this period is very interesting for us because it's the time of the changes of the creation of a new statehood on the territory of Old Rus. This burial mound was cremation, and it richest burial mound. As you can see, a lot of items, weapons, coins, some artifacts with ritual application was found, and at the beginning of 20th century, all of this collection was present to historical museum and keep there more than 100 years. Sorry, the wrong side. Yes, we use the main. Our results was imaging, and we use two modes. First of all, it's interoscopy, when we make some individual projection at the certain position of the sample, and if the condition, if the state of our artifacts allows us, we make tomography. First of all, arrowhead. Oh, sorry. As you see, it's sorry. This small object, why it's interesting? On the first stage, the restoration of historical museum found the traces of the decoration, and as we see from synchrotron tomography, it's floral decoration. And what useful information we receive from the comparison and complex using of neutron and synchrotron. As you see here, we see different contrast in the during the tomographic slices. From the elemental analysis, we know that all these metal base containing iron, but the diffraction shows us that we don't have clear iron. We have some oxidation and hydroxidation of iron. And compare what we can see. This contrast layer, it's oxide film, and due to this film, we can study this object, and this object we can take in hand because it's stable compound, it's thick layer, and it's this layer of oxidation save for us this artifact. And what we can see in neutron, we see another layer with contrast, and we understand that this is traces of the corrosion of the metal base. And as you see, this oxidation film keep the grooves used for inlay during the decoration. And traceology analysis shows us that this was specifically primary prepare grooves before inlay, and only after that inlay in the form of copper or copper alloy wire was introduced inside this arrow. This is a reconstruction of view this artifact. And the other artifact from the same place was the spearhead. The main interesting part of this spearhead is the sleeve which containing some decoration. The form of this decoration is rhombs and triangles. Decoration was made of wire, copper or copper alloy with thickness of 300 of micrometer. And when we study, when we see another slice of this decoration, we see some windings, as you see. So wire was winding. And here you can see the traces of cleats that was used for fixing the spearhead on the spear shaft. And the reconstruction of this decoration can be like that. Another task where combination of neutron and synchrotron study will be very useful for us. It's SWOT fragment. And a combination of this information allows us to see the part of inspiration on the blade of this fragment. And here you see that partly it was clarifying by restorators, but here we didn't see any traces of that things. And now we have another question. Could we find the second part of this sword, and could we recognize the inside this mixture, a lot of components, the inspiration, other letters of inspiration. Unfortunately, I'm not too fast, but the another interesting objects, it's artifacts with a known application. And first of all, it suggests like part of spearhead, but after the clearing, we see some festoon edge without any sharpening, so it couldn't be a weapon. And elemental analysis shows us that this is iron metal base, and bright drops, it's silver. And after the study of the first big part of knife, we see the same festoon edge, we see clear blade, and we didn't find any thinking or sharpening of the blade, so it's not a weapon. On the handle, we see the beads, and cleaning of this object really show that. On this unknown applications subject, we see some special cover plates, and our studies show that it was interior intervivus repair, because as you see, here was gap, and these plates cover that gap. So it was very estimated object. And then we see here some Scandinavian decor, and as you see here, logical end, some traces of breaking. And absolutely another subject show us that we have a lot of cracks, so we cannot clear that subject. And we see the same type of the decoration with another logical end. The another interesting information that here we see some traces of diffraction during neutron tomography. We see, here you see some blinking. It's traces of diffraction, and comparison of neutron diffraction from these two areas show us that we have some crystals of alpha iron inside. So what about reconstruction of this object? We see interesting configuration. We see very close size of the festoon, and we have asymmetrical elements, and we can suggest, and our colleagues from historical museums agree with us, that it could be possible that here we have some lost part with equal one elements, and the style of these reconstructing ornaments is close the Mamin style, which has dating at the end of 10th century. But what about handle? And here we can compare these two objects, and we see the same form, but here we have handle. So we produced that type of reconstruction. We suggest our colleagues from Historical Museum now have very intensive discussion with specialists from 10th century, from medieval period, and the first and main hypothesis that this is sculptures, so it's symbols of power. Another objects, metal and ceramics artifacts from Institute of Archaeology. I should finish my presentation, so I will be very fast. First of all, it's ceramic head, and some the most interesting results that we have two variants. It's the serial production, which produced by pressing, or this the individual item, and we see some traces of sculpture working. Here you can see that it's not only one. Here two layers of adding these sculptures. So we suggest that this head is individual object with like state of art. Very interesting object now we are studied. It's icon with animal decoration, and the main question how it could be. We have only in big part metal walls, but we haven't walls here inside this plate. And for eliminated the situation of sum of summing two pictures, the synchrotron tomography was made at the grazing incidence scheme. And what we can see, this is the slice on the depth of 115 micrometer, and we see that we have it's neutron results. We have some vertical lines, and we suppose that it could be walls. No, it's not walls, it's grooves with some soil or something like clay filling. But in one, we have two big and a little bit smaller parts. The traces of the walls, here you can see it's hidden walls, and they have another position than we see now in the colored plate. And perhaps it is evident of two stages of fabrication. Why the master used two stages, we don't know, and we try to study that. So our studies of these objects are under progress, and some interesting information we receive when we study 3D models of these small parts of walls. We see here traces of the broken. So perhaps it could be that master removed these walls specially. And very bright, very bright results we receive for cross reliquary, or if we use old name of this crosses, encolpions. They have two leaves and small free space for reliquum. And what's the question? Most of them found in close condition. And you have two variants. You don't touch it, or you broken it to see what is inside. And we create a the protocol where we compare synchrotron and neutron tomography, and detailed study some details of construction. And if we see that this in that sample, you see that crosses is broken, so we have the places for soils, for clay. But if we have unbroken crosses, we can conclude that it will be good to open it and to study what is the inside of these crosses. And now our protocol is used for current funds during the excavation. And of course, we have a lot of collective and a lot of researchers which involved in this study. And thank you for your attention, sorry.
If nobody wants, maybe I have one, most from an organizational point of view. When you combine neutron with synchrotron, do you manage to have beam time, let's say, in consecutive days, or do you have to bring the object?
Not exactly consecutive, because first of all, it will be better to make a synchrotron radiation study, because after that our objects could be moved to neutrons, because after the neutron study we have to keep it in special places 1 week or months. It depends on the size and the composition of these objects. So of course we connect this type of studies. We we have some application or proposal for this study, and we because if we have these objects, sometimes it could be once per year. So we have to study all that we can.
Yeah. Okay. Thank you.